If you would recall, we've been playing the vector calculus game, and we've been focusing on line integrals and flux integrals. And line integrals and flux integrals are both based on the dot product. The way we're going to interpret the dot product is how much of the vector field is going in the direction of the curve, or how much of the vector field is going through the surface, perpendicular to the surface. The dot product tells us how much one function is going in the direction of, one vector is going in the direction of the other vector. It's the component of the first vector in the direction of the second vector. Component of the first vector parallel to the second vector. One of the things that we care about when we're looking at dot product is angle between vectors. So we have two very similar constructions with line integrals and flux integrals. I've got the vector field doing whatever the vector field is going to do. I can have some curve running through space or running through the plane. And I want to know how much of the vector field is going in the direction of the curve. How much of the vector field is going in the direction of the curve. The direction of the curve, that's why we have the dr. That's where the dr comes from. That's tangent to the curve. So that's the direction of the curve. Since we want to know how much of the vector field is going in the direction of the curve, we find the dot product. That will tell us the component of the vector field parallel to dr. So f dot dr that'll be the component of the vector field parallel to dr. And that's the direction of the curve. In a surface integral, we are making the same calculation. But instead of having the direction of the curve, we're going to have normal to the surface. How much of the vector field is flowing through the surface? In this case, that through the surface part, what amount of the vector field is flowing through the surface, we're going to look at the amount of the vector that's normal to the surface. That's our dA vector, normal to the surface. So the dot product is telling us the same thing, f dot dA is the component of f parallel to DA, but parallel to DA is normal to the surface. That's just perpendicular to the surface. Good question. How's everybody okay? So what kind of problems can we come up with to talk about flux integrals? We want to come up with a simple problem that we can start making adjustments to. One of our favorite examples to use is to imagine water flowing through a pipe. So we imagine the vector field as water swirling around or as wind swirling around. And we're going to put a surface into the water or into the air. And we're going to see how much water or air flows through that surface. We want to simplify this. So let's think about water flowing through a pipe. Let's suppose that the vector field is just going in one direction. And let's run it into something perpendicular to that vector field. So here's how we're going to simplify things. First, we're going to scroll. Here's how we'll simplify things. The vector field is all just going one direction. So everywhere in this pipe, the vector field is all going just one direction. Constant. So we're going to imagine the vector field as constant speed of water through the pipe, even close to the edges of the pipe. The water is not getting stuck on the edges of the pipe and slowing things down. So we're going to take away, would that be friction? I don't know. That sounds like physics. Because there's going to be friction between the water and the pipe. So the water next to the pipe is going to get slowed down. You have some scrape along the pipe and then stuff in the middle and roll time. Is that how it works? I'm no engineer. I know I took fluid dynamics in my history, but I mean, I can't even picture it in my mind. I can only see it on my transcript, like fluid dynamics. I think I got a B. It's like, well, here you go, fluid dynamics. I can't even picture the professor. I can't picture the room. None of it. It's all gone. I don't know what happened to it. I can picture my Calc 2 professor. This is in 1990. Yeah, I started at 89. Calc 2. spring semester of 1990. 30 freaking years ago. I remember the room. I remember walking to the building. I remember what the professor looked like. All of that. But, you know, I only remember a third of the physics. Physics is brutal. I remember in physics 1, I was devastated because I got the first test back. I had like a 65%. I'm like, holy crap, I'm terrible at physics. I had the third highest grade in the class. And I looked around, so I go, man, I did terrible. How did you do? And my friend got like a 7. 7%. Not 7 out of 10, 7%. And I go, oh, I guess I can picture that guy too. I can picture the room. It was one of those lecture halls. I can picture what that professor looked like. I can imagine the whole thing. Fluid dynamics? No. No. I remember my Cal 3 professor. That mainly because he like looked like Winnie the Pooh. Like seriously, he was kind of like short, kind of like, and his face was kind of pulled out a little bit, kind of like a bear, a little muzzle. And he's kind of short and pudgy. And then he walked in, and I turned to my friend, and I'm like, oh, dude, this guy looks like Winnie the Pooh. He had an incredibly classy move. I was 18, so naturally, I was an idiot. You could tell I was an idiot because I was an 18-year-old male. So that's like, Your Honor, I present to you the driver license of this person in 1990. Oh, born in 71, make him 19? This guy's an idiot. So no question about that. But then the problem was he started talking, and he sounded like Winnie the Pooh too. Holy shit. He sounds like Winnie the Pooh too. And I think he heard me. I wasn't sure. But that made me have to avoid that class for the rest of the semester. I'm like, well, I guess I'm learning Cal 3 on my own. So anyway, maybe that's the reason I don't remember if the water is going to slow down when it's close to the pipe. But the point of this problem is to simplify things to work on it. So don't be complaining about physics to go, oh, we're going to ignore air resistance. We're going to ignore friction. Not forever, but at the beginning, make it simple. Simplify the problem, and then see how other things stack onto it, right? If you got a bunch of people playing D&D and it's their first session, they've never played a tabletop role-playing game, you don't start them out at level 5. There's too much to think of. They can do too many things. You start them off at level 1, where their list of things to do is, I can attack, or I can run away. And that's it, done. Keep it simple so they learn the ideas. Then you start throwing extra stuff in there. You know what I mean? What are we talking about? Oh yeah, so we simplify the problem. We're gonna imagine water flowing through a pipe. We're gonna ignore friction, so the water is flowing the same everywhere. And we're gonna see this water just go through a surface our surface is going to be a cross section of the pipe perpendicular to the flow of the water. So we're going to imagine putting a surface there, some kind of filter that lets the water go, and we're going to see how the water flows through the pipe. And then we're going to change things. So in this case, normal to the surface is the direction of the water. Normal to the surface is the direction of the water. Then we're going to make a change. We'll say the first surface that we're going to deal with let's call that S1. That would be our baseline problem. Step 2 is we're going to take that cross section, that surface, we're going to keep our vector field constant. And I'm just going to take my cross section and angle it. Our second surface is also going to be a cross section, but it's going to be at an angle with the pipe. So instead of taking a circle straight up and down, we're going to angle the surface. If we don't like this representation, if we're wondering what shape is that thing going to be, we have an angle. What kind of shape are we going to get out of that? If you want to simplify things further, you want to drop the problem back one level. Go to the math store and get some rectangular piping. That way the area will be easier to calculate. You won't have to worry about what happens to that shape. So you won't need things like area of an ellipse. One of the things that we're going to need to know is the area. So if we want to simplify things, this would be a good place to start. Start off with a simpler area. I say you have to go to the math store because at the math store, we get all kinds of weird containers for stuff. Think back to Calc 2, and it said there's a tank in the shape of an inverted cone. Like, well, who's going to build a tank in the shape of an inverted cone? And then put water in it. Or my favorite, the hemispherical pool. I'm going to put that much effort into making a pool hemispherical. Seems strange, but there it is. So we can do the same thing here. Have S1 be perpendicular to the flow of the water. And then we'll put S2 at an angle I don't think I drew that. This is why I don't draw things. So we can make an analogous problem with our second surface at an angle with the water flow. Questions? Take a minute and think about what this integral should represent. And we'll start with that first one, the cross section of the pipe perpendicular to the flow of the water. So in this picture, the water is flowing, and this is flowing through the pipe, and this is the speed of the water. So this is going to be measured at some kind of meters per second. The cross-sectional surface, the cross-section of the pipe perpendicular to the flow of water, that's going to be an area. We're looking at the flow through the surface. So we're imagining the vector field as some velocity, we measured in meters per second. And the cross-section of the pipe, that's an area, that's a surface, and that's going to be in square meters. If I multiply these two, if I multiply the meters per second of the vector field and the square meters of the area, the vector field speeding along in meters per second, and the area being square meters, we'll get cubic meters per second. So it looks like what this is going to tell us is the speed of the water through the pipe as volume per second, rather than length per second. This will be how much volume is going through the pipe. Let's think about what that means for our calculation. The water is going through the pipe at a certain volume. If it's a nice constant speed all the way through the pipe at all points, the water is going through the pipe with a constant volume per second. So how we measure, or how we, what surface we put in there, our flux integral shouldn't change. Our flux integral is going to tell us how much water is going through the pipe. Just because we are looking at a different surface, that shouldn't change how much water is flowing through the pipe. Notice that our cross section here, with the water is flowing normal to the surface that we're going through. We're going through a section at a certain area. In S2, where the cross section is at an angle with the pipe, that's a larger area. But the water's not going through any faster because we're not going to take the water flowing through the surface. We're finding the dot product. how much of the water is flowing perpendicular to the surface. That's what we're going to care about. So we have a larger area, but we're imagining the water slowing down because it's not perpendicular to the surface. So if we think about what this water flow problem could represent, even though our angled cross-section has a larger area, we're not measuring the full force of the water flowing through it because the water is not flowing normal to the surface. So the area has increased, but we'll see less speed through the surface. Questions? So what we'll conclude is that full integrals should give us the same value because our vector field is constant. And even though our cross section has changed in area, water flowing through normal to the surface is less because it's flowing at an angle. Questions? How's everybody okay? All right, so for this problem, I want you to think about what we would need to know and how we could make this calculation. How does calculus enter into it? How does the calculus thinking enter into it? Remembering that we're integrating. Integration is multiplication, where one of the factors is variable. I have constant factors here. How does that change things? What do we do when we're integrating? We turn our multiplication problem into an addition problem by assuming things are constant for some small pieces of area. And as usual, the big question when we're dealing with calculus is how we change from our discrete sum to a continuous sum. Calculus is the study of infinity and the difference between the discrete and the continuous. Questions? Comments? I guess my big question is, this took longer last time I did this. Why am I more than 15 minutes left? I probably got more distracted last time I did this. All right, that's going to do it for today. I will see you all on, I want you to think about this problem. I'm not having a meeting tomorrow. So that's it for today. That's it for this week. I'll see y'all on Monday. Everybody have a good weekend and thanks for playing.